that in order to sketch the graph of the function, we have to go through all of these points. Yeah, that means make sure that we know we can address all of them. That section will involve function. This section will involve the derivative. This section, if you can guess, involve the second derivative. We also have a symmetry, but we will not focus like so much of the symmetry. I have to mention this, but we don't have to focus. We will not check this so deep, like in details. And then having all of this information, I hope we can sketch the graph. That's what I would like to do. I would like to take maybe one function and go through all of this. And I have lots of functions in this presentation. You may try later, take different function and do this. Okay, but what we don't know, we know the domain, we know the x and y intercept, vertical, horizontal asymptote. Yes, I have one exercise also. We will do this. You know this definitely. Slant asymptote. And we didn't talk. That's I will talk before we start. I will talk a little bit about the slant asymptote. This section, we know everything. This section, we know everything. Okay, let's look at the slant asymptote. However, yes, I have this symmetry. Yes, but just really quickly, we will not investigate this, but just to know that function may be even, meaning that is symmetric with respect to the y-axis, yeah, the mirror image, even function, and that's the condition. The value for x are the same like value for negative x, of course, positive, negative part. We may have odd function, but odd function is not symmetric with respect to x, because if we will have something symmetric with respect to the x-axis, it will be not a function. Odd function, it's symmetric with respect to the origin. When we will take a graph and rotate 180 degrees, it will be the same graph. That's the examples. That's just like random, yes, random curve. And yeah, and what is like the condition, the equation, value for x are exactly the same, like negative value for negative x. Yes, like meaning, let's take maybe x cube. X cube is a nice example. Okay, that means value for 2. What is the value for 2? Can you tell me if this is x cube? Value for 2 is 8. Yeah, is somebody helping me? You know that I need help. I need help because 2 cube is 8. Now, value for, we can see negative 2, negative 2. That means value for negative 2, oh, a little bit, it will be negative 8. But when I put them together, value for 2, value for negative 2, looking at this property, I cannot say they are equal. No, that will be odd. No, that will be even. Value for 2, the same like value for negative 2. But I have to make it odd, negative. Because if this is 8, this is negative 8, with extra negative will make positive. This is negative 8, but I make them equal. That means just showing this. But we will not like check this deeply. No, but we have to know. Okay, now, periodic function also could be the case. We will not investigate in this section this deeply. This is more for trigonometric functions. But periodic function means that value for x is the same like value for x plus the interval, the period that function repeats. For instance, 2 pi is a good x interval, like the period, to repeat sine function or cosine function, or pi, tangent, cotangent. Okay. Slant asymptote. That means we will try to find the slant asymptote, and I have the definition, but I can just show you how can we find. A slant asymptote is when we have a function, the blue curve is a function, and we will draw an asymptote. The distance, yeah, in this case, I can call the vertical distance between value of the function, f of x, minus the value of the line, which is mx plus b, must become 0. Do you see this? F of x minus the asymptote, the vertical distance. This is that distance. Because it will be smaller and smaller and smaller and smaller, that means will become 0 as x progress to the infinity. That's the definition. But now, how we can find out this mx plus b, how we can find out that line that will represent slant asymptote. We have a nice method because we will only look at the rational function, okay? The ratio of two polynomials. And if you look at the rational function, if the degree of the polynomial from the numerator, the top, is one number greater than the denominator, that's the case for slant asymptote. That's it. Okay? In order to, and then we will identify, okay, this is the slant asymptote situation. Now, how can we find out? We can just divide, long division. Take the top, divide by the bottom, and that quotient will be linear form because they differ in 1 degree. That's when we will have mx plus b form, and that quotient is the asymptote. Okay, no more additional information. Long division, we can see one more number greater than the denominator, the numerator, and the long division. And this is, for instance, your question from the midterm 2. Find the slant asymptote. Do you think this is the case for the slant asymptote? X squared plus 3x plus 2 over x minus 2. Do you recognize? Because I might also ask you, does this function has a slant asymptote? And you can tell me yes on the chat box. Small signal. I know that you can hear me properly. Don't be shy. You posting, you texting, you, unless you can't hear me. Okay, does this function has a slant asymptote? So quiet. Yes, Craig, thank you, Joshua. Yes, because the degree on the top is greater by 1. Okay, let's do the long division. Middle school, x squared plus 3x plus 2. And we will divide by this x minus 2. Let's start. X squared divided by x is x. I can write above the x. Now we will multiply back. X times x times negative 2. X times x is x squared, but I will subtract. X times negative 2 is negative 2x, but I will subtract. I'm changing the sign. X squared minus x squared 0. 3x plus 2x is 5x, and dropping down the other number. Okay, let's repeat the process. 5x divided by x. 5x divided by x is 5, positive 5. And then the same thing. I will multiply 5 by x, and I will multiply 5 by negative 2. 5 times x is 5x, but I'm subtracting. 5 times negative 2 is negative 10, but I'm subtracting. 0, 12, 12 is the remainder, we don't have to, but this is the quotient. That quotient is the asymptote, slant asymptote. That's it. Such a nice question. Okay, that means I don't know exactly how this function looks like, because the point of this section is, but I know that x plus 5 will be the slant asymptote. Negative 5 and 5, a little bit smaller. And also what I know, what number is not in the domain of this function? What number is not in the domain? Can we tell what number is not in the domain? This is just asymptote, of course. We have to 2, yes, that means 2, I don't know. Do you think we will have the vertical asymptote at 2? Because x equals to 2, yes, is not in the domain. We may have a vertical asymptote at the numbers that are not in the domain, or we may have removable discontinuity. That's how we can check. This is also part of this section. How we can check if this function has a vertical asymptote at 2. Yeah, I don't know, I just draw it because it's not in the domain. We have to find a limit. Yes. Limit as x approaches 2, let's say from the right-hand side, of this function. And please tell me, can we get this limit? let's do the direct substitution. Of course, in the denominator, we will have 0 because the number is not in the domain, but it's just small number. This is my symbol. Okay, do we have 0 over 0? If we have 0 over 0, we have to find a common factor, cancel out, and then we will have a finite number, most likely. And then will be removable discontinuity, not asymptote. But I don't think we have 0 on the top. We have 4 plus 6 plus 2, 12. A number over a small number is a big number. That's mean on the right-hand side, function goes to the infinity. It's mean, I don't know, I'm just guessing. I'm just guessing that this will be the shape because function must go and I don't know, maybe something like this. I don't know. I'm really guessing. Of course, it's maybe slightly educated guess, but because we have to respect the asymptote, and that's what we find out. Function goes to the positive infinity on the right-hand side, and just one-sided limit is enough to say yes, this is a vertical asymptote. That means x equals to 2 is a vertical asymptote. Good, yes, good analysis. Do we know the y-intercept? What is the y-intercept? X is 0. Can you remove 0? X? Really quickly. 2 divided by negative 2. Negative 1. I think I'm right. I mean, with my graph. Okay, that's just, tricks like this will help you to pick the right graph on the test. Okay, slant asymptote was the point. The side question was the vertical asymptote. Because of the infinity. Excellent. Let's maybe take this function and let's go through and get the graph. Let's get the graph. And what we sometimes can do, we may provide for you, and actually we will, if we asking you to analyze all of these these points, these guidelines, for the function 2x squared over x squared minus 1, we will provide the first and the second derivative. Because you may notice if we messed up the first and the second derivative, then we will mess up the whole analysis of this function. Okay, that means for this type of question, we may provide first and the second derivative. Okay, so let's start. You will help me. We have to answer all of these questions. Maybe not this one. Okay, let me ask this. Does this function has a slant asymptote? Does this function has a slant asymptote? 2x squared over x squared minus 1. Oh, come on. I'm supposed to have lots of answers on the chat box. No. Only one no. Okay, everybody. Can everybody type? You can type. Yes, thank you. Of course not, because the degree is the same. That's we do not have the slant asymptote. Okay, that's my, thank you. Yes, I have to see my students. I have to see my students through beautiful discussion posts or maybe through involvement in the session. Okay, domain. What's the domain of this function? All of the numbers are in the domain or maybe not? Please type. And I will say positive and negative 1 is not in the domain, which I can maybe say x belongs to from negative infinity to negative 1, from negative 1 to 1, from 1 to infinity. We may see negative 1 and 1 is not good. Okay, x-intercept, if y is 0, if the numerator is 0, it is at 0. If x is 0, the y-intercept must be 0. That's the origin. Yes, that's okay. Vertical asymptote. The potential candidates are the numbers that are not in the domain. But we still have to be careful because we have to find out the limit. If the limit at 1, right or left, or negative 1, right and left, if this limit is infinity, then yes, they are a vertical asymptote. If the limit is not infinity, they are not asymptote. Yeah, maybe removable discontinuity. But algebraically, what we can do, we can look at this function and we can see, because I have to find a limit, let's maybe pick one from the right. I have to find a limit, and let me factor out, yes, at infinity. And we may notice x equals to 1, x minus 1, that's the 0, if x is 1. We cannot cancel out. We will never remove that 0. If we not remove, we will always have a number over a small number. That means it will be infinity, positive or negative. I think will be positive in this case. Yeah? And the same for negative 1. You can see we do not have the same factor on the top. If you will see the same factor, x minus 1 or x plus 1 on the top, we can cancel out, then it's no more 0 in the denominator, no more infinity. Function is still undefined, but it will be, excuse me, open circle, removable discontinuity. That means, yes, they are vertical asymptote. Yeah, you can picture vertical asymptotes. 0, 0 is the x-intercept. You may start imagining the function. Okay, horizontal asymptote. Does this function has a horizontal asymptote? For the horizontal asymptote, what limit we have to find out? How function behaves at the endpoints, limits at infinity. And I think at positive infinity and negative infinity is the same limit. What is the limit? Please tell me. 2x squared over x squared? The same degree ratio of the leading coefficient. That means horizontal asymptote is 2. ... You can imagine a function, vertical asymptotes, horizontal asymptotes. Where is the graph? Okay, and at least I didn't actually finish this. Maybe I should finish this. Let's just, because we do have a limit on the right-hand side. That's we know where the function goes. Limit is 1 from the left-hand side. I'm just checking if we have time, because I plan it a lot. Left-hand side. On the left-hand side, we will have negative infinity. That's we know how function behaves. And the same for negative 1. Please tell me, what is the limit as x approaches negative 1 from the right-hand side of this function? Positive or negative infinity? Definitely infinity, because 0 stays in the denominator. Dividing by small number is a big number. Okay, positive on the top, that's we have positive on the top, negative 1 and negative 1 is negative. Negative 1 plus 1 is 0, but what's 0? Negative 1 from the right-hand side is negative 0.9 plus 1 is positive. Am I right? Yes, positive, positive, negative, negative infinity. Okay, and then limit, yeah, because that's the proper. On the left-hand side, it's negative 1.1. Oh, that's 1. Okay, it will be, I know it will be opposite because nothing is like squared. Okay, we have all of the situation, positive, negative, negative, positive. Okay, and the vertical asymptote too, at positive, negative, the same. Okay, we did the function. Now the first derivative. Let's find critical numbers, increasing, decreasing, local maximum, minimum. Do you see critical numbers? Now we're looking at the first derivative. Wait a minute. Okay, let me check. What was the first derivative? Negative 4x. Negative 4x, x squared minus 1 squared. Okay, critical numbers. Critical numbers. X equals to denominator 0 and numerator 0. This and 1 and negative 1, but 1 and negative 1 are not in the domain. But in order to analyze, to perform the first derivative test, I will put critical number, but we can also put asymptotes, because even if they are not in the domain, they are not critical numbers, but function may change the sign on both sides. And if, I'm sorry, derivative can change the sign. If the derivative is changing the sign, function is increasing or decreasing. We cannot miss this. Okay, let's test the sign. If x is 2, yeah, I'm looking at this formula. If x is 2, actually denominator is always positive. Then this is negative. If x is 1/2, negative. If x is negative 1/2 times negative 4, positive. Negative 2, negative 4 times positive 8, positive. Okay. Then function is increasing, increasing, decreasing, decreasing. Does this function attains local maximum or minimum? Yes, we can see increasing and decreasing. Local maximum at 0. Yes, I hope you're excited. I'm excited that we can see. And did you notice something? Even that, I can even say primitive like arrows, increasing, decreasing, and this is asymptote. And look at this, this is probably the shape of the function. Yeah, if this is the y-axis, and actually that's supposed to be 0, 0. Yeah, like we can use every single increasing, decreasing, because 0, 0 was the x-intercept. Yeah, we have to connect all of the dots. Then we never lost in the city, in the big city. 0, 0, and now increasing, decreasing. On the left-hand side, limit was negative infinity. On the, right-hand side at -1. Left-hand side at 1 was negative infinity. Works perfectly, perfectly. And we're respecting asymptotes. It's a little bit complicated on this side, but at least we have extreme values. Okay, we are done with this. And now the second derivative. Of course, that's the intervals, yeah, increasing and then decreasing, decreasing. What is the second derivative? Second derivative is 12x squared plus 4. 12x squared plus 4 over x squared minus 1 cube. I think cube, yes. Okay, we're lucky the formulas are provided. Okay, we don't call critical numbers, but we need these important points for the second derivative, which is exactly the same. We have to find out where is 0, and we have to find out where the second derivative is undefined. The same for the critical numbers, first derivative, but I didn't write. Okay, for what values second derivative is 0? If the numerator is 0, right? If the numerator is 0, 12x squared plus 4 equals to 0, we have no solution. Okay, because 12x squared plus 4 is never 0. No solutions. And fraction is undefined if the denominator is 0. Denominator is 0 if x equals to 1 and -1. However, they are not in the domain. That's we do not have any turning points, probably no inflection points. We have no solution. But in order to test concavity, okay, we do not have any numbers, but we will still put the asymptote. Okay, asymptotes. And do you see what is happening between -1 and 1? Is function concave up or concave down? Between -1 and 1, it's kind of my guessing, but looks like concave down, right? That means the second derivative is supposed to be negative. Let's check. Let's pick up a value between -1 and 1, 0, good number. When we substitute 0 here, we will get negative number, yes. Negative number. When I substitute 2, 2 squared minus 1 is positive. And when I substitute -2 squared, it's also 4, it's also positive. Yeah, you can just take the test value. Okay, then function is concave up, concave down, concave up. And we knew it, that is concave down. No inflection points, no inflection points, because we do not have -1 and 1 are the asymptotes. Okay, that's we are almost, yes. Do I have the graph, but I would like to, you will see the graph? No, don't look at this. I know that some of you are not looking. Okay, some of you are maybe cooking or singing. Okay, that's me. Now let's try to get the graph together, because this is always the excited part. Let's put everything what we know. What you can do, you can pause the video, you can don't look at the solution and try to, yes, put all of the information. We did find out that this is asymptote, vertical asymptote, okay? We did find out that 2 is a horizontal asymptote. Oh, my 2 is a little bit lower, it's fine. 0, 0 is the x-intercept, y-intercept, and also a maximum. I mean, actually, we knew that this is limit is negative infinity. On the right-hand sided one, I think limit was positive infinity and positive infinity. Okay, and we also know, let's look at this, from negative infinity to -1, function is increasing and concave up. Do you see concave up and increasing? If the function is concave up and we have a horizontal asymptote, function must be above the asymptote to satisfy this asymptote. Okay, above. I cannot put below. That's mean, yes, that's the graph. And now the same thing. Function is, is function decreasing? Yeah, it is decreasing. Oh, well, decreasing, concave, that means it will be that shape. Decreasing, concave up, again is concave up. For the horizontal asymptotes must be above. If function will be concave down, then will be below the horizontal asymptotes. I think that's the graph. And this is, of course, 0, 0. We're respecting everything. We did the beautiful. And it's actually symmetric with respect to the y-axis is even function, but we're not looking at this. I think it's a nice graph. And now I can show you. That's what I didn't want to show. Okay, it's a nice long process, but it's so satisfying that you can get the graph, yes, of function like this. Okay, good. Now, any questions? You're so quiet. Oh, I'm loud. I don't know if you can tell, but I'm loud. Okay, now what I have more formulas. I don't have the work, but you can try the work. But what I have the graph. You may check. I have another one, and I have the graph. Oh, this is example number 4, yes. And then that's the graph. I have another one, and that's the graph. I have another one, that's the graph. You will forget the graphs. Or try to get the graph. This one, you have the additional video. We will not do this one. Okay, let's do a couple of those, because that's good for the test. Because how we can really, yes, you can't really draw a function and provide for us. That will be, yes, that will be excellent. But we may ask you this way. Having a couple of data, couple of information about the function, which graph satisfies this? Let's try to maybe eliminate. By elimination is a good process. Okay, what we know, yeah, that means this graph must one of the graphs satisfies all of the conditions. Okay, we know that the limit at negative infinity of the function is positive infinity. Then at negative infinity, we have no horizontal asymptote. At negative infinity, function goes up because that's y values. Which function goes down at negative infinity? As x goes to the negative infinity, which function goes down? I don't know, how do you see me, the mirror image? This function goes down and this function goes down, right? We can see they going down. They're not good because we have to have up, positive infinity, positive infinity, positive infinity. Okay, now as x goes to the positive infinity, the limit is 1. Horizontal asymptote, it's 1. But actually this one has a horizontal, horizontal, horizontal. We cannot eliminate. Okay? Now, f of -1 and at 1 is 0. X-intercept, the value at -1 and 1 is 0. Which function has -1 and 1, 0? Only, yes? It's supposed to be only, mathematically. I think -1 and 1, -1 and 1, -1, 1, oh, and 3, not good. We do not have that x-intercept listed. That means B and C. Okay. Derivative is at 1 is 0. Looks like, yes, at 1, we do have horizontal tangent. That means both of them satisfies this. Now, okay, what's the difference between B and C, actually? Between 0 and 2. Do you see this? Between 0 and 2, B is increasing, C is decreasing. Let's check this out, and then we are done. First derivative. That means I'm looking for the first derivative. First derivative is telling me that is less than 0, then function is decreasing between -infinity and 0. That's good, -infinity and 0, and is decreasing between 2 and infinity only. Yes. Then it's not decreasing here. It's not decreasing. It's actually increasing because it's only decreasing on that. Okay? I think it's a nice exercise. And you will have fun finding the right graph. Or I can ask you this way. That's the same. You can try. We can ask this way. Okay, just giving you the formula and then trying to, instead of the conditions, C and E. Okay, are we good? Are we excited? Please remember, the biggest currency in the world is your energy that you can give to somebody. Nothing else matters. Nothing. I know. A little bit of philosophy. Oh, Joshua, you know the answer. You're not wasting time on philosophy. Okay. It is easy. Oh my gosh, it's the examples. I think it is. Okay. First of all, what I will see, does this function has a slant asymptote? Does this function has a slant asymptote? X cubed versus x squared in the denominator. The degree is greater by 1 on the top. Yes, thank you, Craig. Yes, that means this function doesn't have a slant asymptote. This function doesn't have a slant asymptote. Okay, at least we eliminated 2. Slant asymptote, it is a case. We don't know what is the slant asymptote. We don't have to find out, but yeah, it is. Now, what is the x-intercept? X-intercept, numerator 0, numerator is 0 if x is 0. 0, 0, oh wow, and we have additional 1, not good. Additional zeros, not good. I don't have to go and check the other cases, I mean other conditions. We good, yes. Joshua, really good. Are you planning to get 100% on the test? Everybody's planning to get 100%.
That is a yes.
Yes, good, yes. You're giving me good, yeah. You're giving me a good signal. You definitely, yes, on the good track. And everybody, I'm not, yes. I just, whoever is giving me the energy, I can tell something. Okay, But we may, I don't know, let me check if we have time. We can maybe do, because I have couple. That means you can also, yes, investigate. Sometimes we need more and more condition, but you know the guidelines, yeah? You know domain, x-intercept, y-intercept, slant asymptote, horizontal, vertical, and then first derivative, increasing, decreasing, second derivative, concavity. That means you may investigate further and further if we cannot eliminate. Okay, but let me leave this one for you because it's fun. I don't want to steal the fun. Oh no, I can create new fun for myself. You can do this one. Oh, the first, second derivative is provided. This one, let's do this one. Find the graph of the following function, because this one is relatively easy function. You can probably get, of course, if we will ask similar question, we will provide 5 graphs. Yeah, we will provide. I don't have it, but I just want to roughly get the graph, not the exact graph. That means this is just polynomial. We know polynomials are just like this. Yeah, polynomials are the nice, and I mean, maybe this, I don't know, but it's just a nice smooth curve. All of the numbers are in the domain. That's what we know about this function, except the domain are all real numbers, all real numbers. Do we know something when we're looking at this? I can maybe start drawing, because then you can, I don't have the graphs, as I said, because we may, but you may start eliminating the graphs. What we know, looking at this graph. Do we know y-intercept? Y-intercept, x is 0. What is y-intercept? X is 0. Eliminate, yes, y-intercept. Okay, that's me. You're looking at the 5 graphs and you're looking where the function intersect y-axis at 1. If it's different, eliminating, maybe will be the only one. Okay, that's we know this. I will not start looking for the x-intercept, because solving this 5th degree polynomial equation, it's not easy. Not easy. We cannot really factor out. That means let's keep the x-intercept. We do have something. Okay, do we know where the function goes? Up or down as x goes to positive infinity? Yeah? The leading term, x to the power of 5, when I take the highest number, I mean big number, x is big, to the power of 5, it will be still positive. That means function will go up. Yes, and at negative infinity, negative numbers to the power of 5 will go down. That means that's at least the endpoints. I mean the end function might go up and down, respectively at positive, negative infinity. You can also eliminate. Okay, but what is in the middle? Let's find the first derivative. What's the first derivative? Please watch me if I'm right. 15x to the power of 4 and 20x to the power of 3. A little bit nicer. What are the critical numbers? We just have to find out where the derivative is 0. I can factor out 5x cubed. It will be 3x minus 4. And then 5x cubed must be 0. And 3x minus 4 must be 0. That means definitely 0. Yeah, it's x0 is a critical point, and x 4 over 3. Actually, if x is 0, the value is 1. Yes, when you substitute. That means this point, but let's check. We can figure out increasing, decreasing. 0, 4/3. And we're looking at the sign of the first derivative. This is the first derivative. When x is like big, like let's say 10, 100, let's say 2, 3, 4, greater than 4 over 3, then the value will be positive. When the x is maybe 1, 3 minus 4 is negative, and when the x is big number, I mean big negative, -1, -100, -1000 from that interval, This will be negative, this will be negative, negative and times negative is positive. Okay, that means function is increasing, decreasing, increasing. And we okay, that's it. And this will be local maximum. Local maximum. It's actually x cubed. That means it will be more flat because it's like triple like value. Yeah? I mean, I think it will be a little bit flat, and this one must be 3/4. I'm just indicating because this will be local minimum. Local minimum. We can take 4/3 and substitute to the value of the function and compute the value. Maybe can we actually make sure, because my value looks like below the x-axis negative. I don't want to spend time, but let's check if this will be positive or negative. 3 times 4 to the power of 5, 3 to the power of 5, minus 5 times 4 to the power of 4, and 3 to the power of 4, plus 1. Do you think it's negative? I think it will be negative because 3 is less than 5, and 5, yeah, even if I will say that 5 is 4 to the power of 5, and this is smaller. No. Let me, how we can figure out. Just in case, if you will have the graph, yeah, for instance, something like this. Do you know what I mean? This is 1, this is still 4/3. That means the condition that we check, it's satisfying local maximum, local minimum. But now the value, the corresponding value is below the x-axis or above the x-axis. Or maybe we can do something else. But no, we will check concavity. Okay, let's figure out without the calculators. If I will factor this out, I will have 3 times 4/3 minus 5 and then plus 1, right? I just factor out this 4. I'm trying to find without the calculator. 12/3. Oh, 12/3. Actually, 4. 4 minus 5 is -1. That means this is negative number. This is negative number, big number. Plus 1 doesn't matter. That means, yes, my graph was okay. This is negative. I don't know what it is. I still didn't figure out, but it's definitely, we can see 4 minus 5. Okay, that means just in case, yeah, if you will have similar question, and that's not an option. This is the graph. Okay. That means even with this nice polynomial, or maybe you have different idea how to find the graph. Yeah? But even if we have these similar cases, that cannot be above the x-axis because we figure out. Okay. Oh, no. One more thing. I want you to tell me this question, and let me check. Okay. Yeah, this question is my last question. I have the graph. Oh, okay. Find all vertical, actually, no, find all asymptotes. All vertical and horizontal and all maybe slant. Okay, all asymptotes. That's supposed to be my question. Find all asymptotes of the function. Okay, x squared minus 1, x squared minus 2x minus 3. Horizontal is easy, right? What is horizontal asymptote? Horizontal asymptote. We may have 2, that's the maximum, positive, negative, infinity. We have to find out the limit at infinity. What's the limit at infinity? The same for negative, because it's minus 2x minus 3. Okay, limit is 1, horizontal asymptote is 1. That's mean you're good with this because it's x squared, leading coefficient. Okay, now what are the numbers that are not in the domain? That's the good candidates for the vertical, just the candidates. Vertical asymptotes. We may have infinitely many. Okay, let's check. Actually, we may factor out. Then we will see right away. Let's keep this one. Who can help me? X, 1 and 3. Negative and positive. Please check. So we can see x 3 and x negative 1. Yes, thank you, Joshua. Are not in the domain. Okay, that's mean maybe this and this, but they are just question mark. They are just question mark because not all of the numbers that are not in the domain. And we remember algebraically, if we can eliminate that factor, that 0 from the denominator, that this is not an asymptote. How we can simplify this function? X plus 1, x minus 3, x plus 1, oh, my writing, and x minus 1. X plus 1 can be eliminated. I'm sorry, this is supposed to be negative 1. Okay, that's mean negative 1, that 0 is, it's still, function is still not defined, but at least that 0 is gone from the denominator. When we compute a limit as x goes to negative 1 of the function, of course, we will simplify. It will be negative 2 over negative 4. Am I right? Yes, it will be 1/2. That means that's no vertical asymptote at this. Yeah, no vertical asymptote because the limit is finite number, removable discontinuity. But you may notice x minus 3 is not cancelled out. It will always give me 0 in the denominator. 0 in the denominator and finite number on the top. It's definitely infinity. 3, that means this is positive over positive 0, positive infinity, and on the left-hand side, we don't even have to do this. But it's definitely infinity. That means, yes, this is a vertical asymptote. Okay, horizontal, make sure that we know horizontal, vertical, only this one. Do not circle the answer right away. No, always check if you can simplify. Does this function has a slant asymptote? This is supposed to be my first question. x squared, the degree doesn't, yeah, no, thank you. And actually, if the function has a slant asymptote, it will not have horizontal. No, that's not, yes, not the case. If we have horizontal asymptote, then it's no slant, unless it's like really, oh, no. Okay, actually, no, actually, yes, we may have a slant asymptote, but maybe just if this will be really piecewise defined function, because maybe for one piece could be slant and then the other formula has only horizontal. Okay, yes, for the piecewise defined function, but for the function like this, for one formula on the entire number line, no slant and horizontal together. Okay, and let's just quickly check. 3 is a vertical asymptote. 1 is a horizontal asymptote, and function goes up and function goes down, yeah, on the left and the right hand side. And at negative 1, the limit is, I don't know, I'm just guessing, the limit is 1/2. I mean, it will be something like this. Removable discontinuity. Oh, what is the x-intercept? I mean y-intercept. Or even x. Am I drawing this? Oh, but negative 1 is not in the domain. I supposed to intersect this? Please tell me why intersect. I have to intersect here, somewhere here. X is 0, then we can see we will have only -1. I can't draw it. -1 over -3, 1/3. Okay, and I think this will be like this. I don't know. We don't have to check the graph, but just to have the scenario, and I have the beautiful graph. Yes, vertical asymptote. We're supposed to have horizontal asymptote because I changed the function the question. Okay, horizontal. Okay, that means please make sure. Oh, yes, 1. -1 is not in the domain. Okay, that means now I think you can enjoy the graphing, you can enjoy the combination of all of this first derivative condition, second derivative condition, and asymptotes, domain, of course, and X and Y intercept. Okay, you can definitely do everything, and you can also treat this as a kind of like an exam review, yeah? Because I did refer a couple of questions that you might have it. Okay, enjoy. Thank you for the participation today, and thank you for your energy. I can feel a little bit. Please give me more, yes, in the following weeks. Thank you, and see you at the next session. Thank you.
Have a good day, ma'am.
Thank you.